matrices. Which have an additional condition for the star. So star plus one more condition, which is determinant of D equal to 4 equal to 1. Okay, so so we actually had some notation for it. So we have ON for orthogonal matrices and SON for special orthogonal. Okay, so these are, we think of these as sets. We'll see later that it's a group, that's an operation.
Hello.
Okay. Yeah.
Sir, what is this star that you just made?
Star refers to D transpose equal to 1. Instead of numbering it, I numbered that equation star. So special orthogonal matrices are star plus one more condition, determinant of D equal to plus
1. Okay.
Okay, that's it. Okay. So star is the same condition of orthogonality. Okay. So for our purposes, I mean for us, for our physics, for our use, for us, n equal to 3 was of interest, was or is of interest. Okay, and I introduce, so if a matrix belongs to SO3, okay, it is also called a rotation matrix. Okay, so that's a fact. Any rotation in 3D, that is n equal to 3, as we wrote there, in 3D can be thought of as a rotation about an axis by an angle, by a fixed angle. Okay, so what one has in mind is some picture like this. There is some axis along some unit vector, and that is rotated by some theta. So I will introduce notation like this. Okay, so this is just. Okay, so this belongs to. Okay, so exercise which will probably be there. I'll give only one example about, say, the z-axis, rotation about z-axis by angle theta. Okay, this you can check very easily. This we know. Okay, this is an example. And so now we want to make use of all these things. So I'm going to define a vector under rotations, also known as S3. Okay, so what we do is we write a vector v more like components. So there is some basis chosen. We have components. See, like examples we saw last time. Okay, so under okay, so so this is how the components of a vector will be some rotation matrix acting on.
Sir,
Yes, go ahead.
someone is asking if this is also true for improper rotations. This mic
No.
is not working.
No. I will get to improper. Improper means determinant -1, right? The orthogonal part. No. At this point, we are only discussing. We'll put that as a next step. Okay. So absolutely. At this point, no. Okay. So it's better to write this like this. So instead of writing it like this, we'll introduce short form notation. Not short notation, just call it notation. So the notation is repeated index is summed over, called Einstein summation over convention. So here the index that is repeated is j, and j runs from 1 to 3, so it's just short form for that. Okay, so this is called Einstein summation. We'll refine it further in this course at this point. Okay, so this is the same as saying summation j equal to 1 to 3 rij vj. Okay, so any object, so the definition is, so let's call this as, so any object that transforms as above under rotations is called a vector. Okay, so this vector is so if you want to qualify things, or sometimes to be more in, one also says vector under rotations. Okay, but this is usually under rotations part is eaten up. You just say it's a vector because of context. Okay. So now comes the thing. So similarly, we can define scalars. Invariant under rotations. So it doesn't transform. Okay, so now we can go back to Newton's equations and write it like this. And qualify things out here. So what is Fi? It's a vector. What is Ai? It's also a vector. What about M?
Scalar.
Okay. Simple exercise. Product of a scalar and a vector is another vector. Okay. So what we have is left hand side is a vector, right hand side is a vector. We can actually rewrite this as a vector equation.
So does the word scalar comes from scalar, which means that it is scaling?
No. Not at all. So we define these equations as EI, which is Fi minus MAI. Okay, so this is the equation. It's also a vector equation, so I give it a vector index. And Newton's equations is
So here does the subscript I represent one of the components, or is it representing the whole vector itself?
it's a so from this viewpoint, it is like 3 equations.
Okay.
Okay, but they're not 3 scalar equations because they transform like a vector. If you have a collection of 3 scalars, they don't form a vector, for instance. Right? Okay. So Newton's law can be written as EI equal to 0. So it's a vector equation equal to 0. Okay. And so that's a simple fact which is easy to see. If a vector vanishes in one frame, it vanishes in all frames. Okay, so example of that is Newton's equations. It says that EI is this vector which vanishes. Okay, and it's easy to see going back to the definition of this thing. So it says that if Vj is 0, you can see that term-wise it's a sum of 3 zeros, so V prime is also 0. It's a very trivial statement, but it's actually a very powerful statement. Okay, so we can so the thing is that this equation is true. So for instance, EI application of this is EI equal to 0 implies that EI prime is also 0. Okay, and actually if you're quadratic, you should say that this is the 0 vector. Okay, but I'm not. So is this clear? Application of this fact. Is this fact clear first?
So EI is equal to 0 is actually 3 equations, right?
Yeah.
Yes, sir.
But it's not a collection. There is a further statement that under transformation, so EI prime is equal to Rij Ej. There's an additional factor. I mean, it's not just 3 random equations. That these 3 equations together form a vector equation. So in that sense, you could I would think of it as they come as a package. Okay, so the thing is, if you have a scalar, so let's do a scalar equation, for example. A scalar equation is something very simple. For instance, let's look at equation of continuity. So rho is some density and J is some current. You must all have seen something like this. Okay, so this is some equation which is S. It's some scalar equation S. Again, you can check if a scalar vanishes in one frame, it will vanish in all frames. So that's the same fact goes through. So S equal to 0 implies S prime equal to 0. Both ways it goes actually. Even here. Okay, but what I'm trying to tell you is that this equation EI equal to 0 is not equal to 3 scalar equations. Is that clear? Because under rotations, S1, S2, S3 mix with each other. Or sorry, E1, E2, E3 mix with each other. So they come as a package. Okay, so now, the thing is that, so with the covariance of an equation, so this is the idea of covariance which will come. Covariance of vector equations, for instance, is the statement that the set of 3 equations are not invariant, you see, mix with each other. Okay, so the statement is the English word for that is, we say that Newton's second law is covariant, manifestly covariant. And that problem is done by, we already did this. First step was to say that, f is a vector and a is a vector and scalar times vector is a vector. So the equation is a vector equation. We already said that. And so an equation like f equal to ma is, it's invariant under rotations. And this is what helped the two guys to match their result at the end, right? It told them that they could change from one to another. But if you have a scalar equation, you will say the scalar equation is invariant. Okay, so this, so you cannot, invariant is fits under covariance, but all covariant equations need not be invariant equations. Okay, that's why I'm saying E1, E2, E3, you can think of them as a package. They form a vector set of equations. Okay, so the general idea is to write equations that exhibit covariance manifestly. Okay, so for instance, for Maxwell's equations, this was not done by Maxwell. But much later, there are a few others. By Heaviside is one important. Okay, so equations like del dot v equal to 0. What kind of equation is this under rotations?
Scalar equation should be invariant.
It's a scalar equation, absolutely. Okay, so if you have an equation like this, this is a vector equation. Okay, so later we will see that Maxwell's equations have symmetry which is much larger than rotations, but at least what Heaviside did was to show there is symmetry under rotations in a very, very manifestly it's explicit fashion. So that's why you want to write things as vector equations and introduce symbols like grad, which is vector calculus. But still, from our viewpoint, all that matters is del transforms like a vector under rotations. We don't care anything beyond that. Okay. So this is the general picture. So now the question is, what improper rotations?
So the Maxwell equations did not look like how it looks in Griffith's.
Yeah, exactly. So it happened only later. Yeah. So yeah, I have some article which gives a long history of how Maxwell's equation. So the way it's written in Griffiths now was not the way Maxwell wrote it. He would have written it in components. Okay. So absolutely. Okay. So what about improper rotations? So now so let's go back to so these are improper rotations are I call them just orthogonal. These have determinant equal to -1. Example was parity, right? on vectors like this. Okay, so the key point here is that everything can be written in terms of parity times of regular rotation. So it's enough to give transformations into parity, and p square is equal to 1. So its eigenvalues. What are its eigenvalues? If a matrix squares to 1, what can you say about its eigenvalues?
The diagonal elements.
Yeah, but eigenvalues will be plus or minus 1. So any matrix satisfies its own characteristic equation. So this is the same. Let's say lambda square equal to 1 implies lambda equal to plus or minus 1. Okay. So there will be two kinds of scalar. We'll call one scalar. We'll just reuse the thing. Another one we'll call pseudo scalar. Okay. This is invariant under parity. And this changes sign. Okay. So now we are going beyond rotations. We are putting in orthogonal. We are looking at parity transformation. Is this clear? This is what we will define.
So what exactly is improper rotation physically?
An orthogonal rotation with determinant equal to minus 1.
No, so I mean physically, how do
Physically, I mean, I don't know what is physically. I mean, here I've given you an example. It's flipping all the coordinates.
Oh, okay, sir. Yeah.
Okay, takes you from a right-handed coordinate system to a left-handed coordinate.
Yes, sir. Yes, sir. Okay.
Okay. Okay. So,
Sir, a scalar has only one number. So what does it even mean to say under parity?
so that's what is a statement of the eigenvalue. So it will be P acting on the scalar, giving you plus 1 or minus 1. So that's all. Okay. We will see examples soon. Okay. So similarly, we'll have vectors. Sometimes called polar vector or just vector. Okay, and we'll have something called an axial vector or pseudo vector. Okay. So again, you have to tell what happens. So this is just transforms like P 1, minus 1, minus 1, minus 1. Axial vector. Does not transform. It's called vector. Which is the same as saying its eigenvalue is plus 1. Okay, that's what it means. Okay, so we'll start with examples. Okay, usual displacement, velocity, acceleration, force, electric field. These are all examples. Any examples?
Torque.
Angular.
Yeah. Angular momentum, for instance, R cross T. For instance, okay. Here's an example. So a key point is that so this is a classic way, cross product of any two polar vectors. Is one example. Okay, and further, another example I'll give is B, the magnetic field. So you can ask, how is it? We will know. Okay, and so let's write one more example, which is a current. Okay, so again I can do scalars. Okay, so rho, which is like say electric charge density. And here J is electric current. There can be other currents, but they are usually all polar. Okay, so rho is something like this. So pseudoscalar. Okay. So classic example is E dot B. Okay, so it's a dot product of a scalar, a polar vector, okay, so these are simple examples. Okay, you can construct more. Okay, but I'm just giving you, yeah.
So why do we call them pseudo? I mean,
Pseudo is
just
it gives
name.
you the it's just a name, but it's a refined. So first we decide whether look under rotations, decide it's a scalar or a vector, etc. And then you add parity to the story, and you add parity
If
to
it
a
is
story.
invariant, then it is scalar, and if it is and
Yeah, if it
it
changes
changes
sign,
on the sign, then it is
yeah,
pseudo vector.
exactly. So
So
here we
what
can
is
see that E changes sign, B doesn't. So E dot B will jump. But E dot E, for instance, that would be a scalar.
So in case of axial vectors or pseudo vectors, can we consider curl of a polar vector?
Yeah, so let's do that. Yeah, good. I wanted to do something like that. So let's try to make sense of something like that. So let's look at L cross B equal to mu naught times J. Let's look at this equation. Okay, so we had given some assignments, and let's write it and see if it is consistent. Okay, so this we said is polar. This is axial. Del is like also axial. This is polar. Okay, so cross product of a polar and axial will become polar, because you want the polar guy will change sign, B won't change sign, roughly speaking. So then you take that, you will get this thing. So this is consistent. Okay, similarly, let's do one more scalar equation. Okay, both are polar vectors.
So we can then say that the magnetic vector potential is a polar vector.
Exactly. Yeah. So B equal to del cross A. So this is axial. This is polar. This has to be polar. So you go back and check that all of the Maxwell's equations, you can put time dependence also back into the problem. You will see that we can consistently assign parity, their transformations under parity. Okay. So
can you tell what is E dot B?
E dot B is a pseudoscalar.
But physics.
Physics wise, you will learn it in your E&M. Okay. Yeah, it is something interesting. Okay. So there are two scalars.
Intensity.
I'll not discuss it here. It's not. I mean, from our viewpoint, it is just that. Okay, you will see that in your E&M course. All I can tell you is that it's not some random combination. Okay, so I mean, for instance, another half epsilon naught E square plus half B square by mu naught. Okay, this is also a scalar under rotations. This is energy density. Electromagnetic energy density. Okay, and rotations. This is scalar, not stochastic. Because dot product of two axial vectors is a polar vectors is a scalar. Similarly, dot product of two axial vectors is also a scalar. Okay, so we can go ahead and assign these things properly. Okay, so I'll pause here. Are there any questions? Okay, I guess not. So we can construct more general objects. And so these are objects which will have, okay, we'll define them.
Sir, why is it called polar and axial?
My history is not very strong. Okay, so these are historical things. Okay, so more general objects. So what we will do is I'll construct something which, okay, defined by the transformation law. Okay, and so we'll start with I'll write something and I1, I2, IR. Okay, so this is some object which has, so in this case I1, I2 up to IR all take values from 1, 2 and 3. Okay, so I will tell you how this guy transforms. So T prime of I1, I2, IR is R, I1, J1, R, I2, J2. R means such little r such matrices. Okay, remember Einstein summation convention holds. Okay, so this is the transformation rule. Okay, so just call, so this thing is R. So the easy way to, the way I think about this is I'll focus on some particular, and let's say I2. Okay. So I2, if you just focus on I2 and forget that all I1, I3 up to IR exist, you see that it transforms, I2 index transforms like a vector. Right? Ignoring all the other terms. Okay, so it transforms like a vector. Okay. So if you take each case by case, then you see that each one of them behaves. So it's like a collection okay. So objects like this defines a tensor of rank R. Okay, so we already know examples. A rank 0 tensor is what? A scalar. Rank 1 tensor
Vector.
is a vector. Okay. Why does somebody want to join like so late? 38 minutes into the lecture. Okay. So again, key fact. If an rth rank tensor vanishes in one frame, it vanishes in all frames. Okay, so again we can have equations which are tensor equations which are covariant. So we can write something, we can have an equation. So this is a covariant equation corresponding to a tensor of rank. So it's kind of very nice. Okay, so covariance. So you could have things like this, and in physics there are examples like this. So I just want to spend a few minutes on the first tensor of rank 2, which is the first non-trivial generalization. Okay, so it will be T I1 I2 according to this. So T prime of this will be okay. So now suppose, so let's look at some properties. Suppose okay, I1, I2, if you exchange the two indices, so we call something, what do you call something like this? It's symmetric, it's called. Okay, we can rewrite this in a slightly different form. We can write it like this: T I1 I2 minus T I2 I1 equal to 0. Okay, so you can view this in many ways, but I can view this as an equation which is a tensor equation of rank 2. Okay, so what does this tell us? If so in some frame, if Ti1 I2 equal to Ti2 I1, or written this way, it's equal to the 0 tensor of rank 2, it will remain 0. So a symmetric tensor is symmetric in all frames. So this is a property which is preserved by rotations. You can go back to this formula and check it, but you can also understand it this way. Both are equivalent. Okay. Similarly, antisymmetric means you put a minus sign. Okay, so I have an ugly exercise. Okay, so Ti1, I2, how many components does it have? I1 can take 3 values, I2 can take 3 values, so this has 9 numbers. Okay, so we can form a column vector like this. I won't write all of it. Okay, so this is a column vector, 9-dimensional column vector. Okay, so let's use some notation. I'll just put it like this and put a under bar for it. Okay, so now what I want you to do is to write this T bar prime will be some matrix times T. Okay, so determine okay, so this has a name in mathematics. You read this as R tensor R. Okay, it's also called Kronecker product of matrices. Okay, so please go ahead and work out what this matrix is. It's very, very ugly, but it's quite useful practice to go back. And so what you will see here is that this matrix, every entry in that matrix will be quadratic in the R's. It won't be linear in the R, these matrices, the entries of the matrices. You have to write that up. Is this exercise clear? Okay. And
So won't T be a square matrix?
which one?
T will not be a square matrix.
T is the column. T bar is this column vector. I'm rewriting it. I don't want to write it as a matrix. Okay. So this is just a 9-component vector. More clever basis, more clever choice would be something like this. Again, it's a 9 by 9 matrix. T11, T22, T33, then off diagonal terms. So T11 plus T12. Okay, so this is a symmetric part, and then the next since I have overshot, no, I have space. Oh, very nice. Okay, so this is also a 9 by 9 vector, but slightly different choice of basis, how we write those guys. Okay, so this is a different choice. But this choice is very nice. If you look at the 9 by 9 matrix, you will find that it's a 6 by 6 block and a 3 by 3 block, which is 0, and these are zeros. Okay, so R tensor R in this basis will look like this. Okay, so please work this out. It's kind of ugly, but it's something which you can do while watching Olympics. Okay, so I would just suggest that you work out. So, yeah, tedious exercise. But worth doing once in your life. Okay, so So what we see is that, useful, it's useful to write all equations as with as tensor equations. Okay, so that they are manifestly covariant under rotations. This is okay, and so examples of I have to give examples of second rank tensors. There are higher tensors, but I'll just give you second rank. Okay. So stress tensor, stress, strain, these are all examples. Okay. That's a remark to make. Second rank antisymmetric tensors. Are nothing but vectors. Okay, because there are three components, you can also check. Okay, so check this. This is very special. This is special to 3D. If you go to 4D, that's not true. Okay, so one doesn't discuss second rank antisymmetric tensors because you can convert them to vectors and work with them. Okay, so for instance, yeah, so I'll stop. I think I'll stop here. And so next lecture, we will do two things. We will look at formal definition of group, and we will also study symmetries of Newton's equations. Okay, so we'll get a new group called the Galilean group, which is larger than rotation. Okay, so we'll study this in next lecture. So I'll pause here for questions and let me stop. Yeah.
Sir, is the moment of inertia tensor or second rank antisymmetric tensor?
Yeah, it is.
Sir, in the Carl equation, how can we show that the del operator refers to a polar vector?
You just do the transformation, no? I mean, nothing. There's nothing special.
Sir, Vera is asking if there is any reference for reading on tensors.
Again, it's a case of I don't think we need deep stuff. I would rather you spend your time writing those 9x9 ugly 9x9 matrices and looking up what is Kronecker product. Okay, the reason is that the tensor method is a fancy way in group theory to construct new representations from old. So starting from vectors, you can construct all the other representations of the orthogonal group. And orthogonal group is very messy, so there's something called a unitary group for which it's cleaner. But so if to me, I mean, it is like a tangent which you can go to no end. And so again, I mean, there are references, but I feel that that's too heavy. The level at which we will need to understand, I would rather you get the intuition behind it, and the intuition behind it, it's like a collection of vector indices, are such vector indices, and we move on. That's about it. Okay, so I don't want to give any references because it's fairly heavy stuff. I mean, like we did, for instance, symmetric, anti-symmetric, we just got done with that. But actually in the orthogonal group, there is still additional factor that actually you can remove that so-called trace of it is the scalar. So what the correct statement is that you get a symmetric traceless second rank tensor, and then you get a scalar and you get a vector. Okay, so it's kind of so if you go to rank 3 onwards, it gets much more messier. I mean, one can do it, but at your level, I think it's not worth it. We don't need those fancy things, and so it's some heavy mathematical machinery which exists. But what we need is something much more quite often we need something very simple, that if you can write an equation as a tensor equation, it's manifestly covariant under rotations, and we are very happy. That's about it. Okay.
Okay, sir.
So pseudo-scalars and pseudo-vectors are tensors or not? They are not tensors.
Yeah, they are tensors.
They are tensors.
Yeah.
So they obey the rules of like rotation and the transformation.
Yeah. So here I'm focusing, when I talked about tensors, I only talked about rotations. So now you have to go back and ask, what does it mean under parity for those guys? So we'll stop at rank 0 and rank 1 cases, which we did. But there are generalizations.
Okay, so reflections and all that.
Yeah, so reflection is also an example of a determinant -1. Yeah. But you can always write it as a parity followed by a rotation. So exercise, please do that, which is to take a reflection and write that as a parity times something. Okay. Yeah, good.
Sir, this is just a question. We have seen scalars, we have seen vectors. A vector is like a collection of many numbers that has properties. We say it transforms into rotations like a vector.
Mm-hmm.
Is there something like people try to put together many scalars and call it something like
No. There's no meaning. I mean, there's no meaning of collection of the random 3 scalars which are not related. There's nothing to it. So under rotations, actually, they have to fit. Here is the thing, right? If something transforms under rotations, it has to be a tensor of some rank. That's what you can always write it that way.